Hello, welcome to another video on differentiation. Today we're going to be looking at some relative extrema problems. So for these types of problems, it's really important that you give a good explanation. And so in this video, I just want to highlight that. The AP graders are somewhat strict on some grading, some things that you have to specifically mention in your explanations for these problems. So even though they're straightforward, students tend to lose points just because they don't explain properly. So today I'll go over how to do that for this problem. So we're finding the absolute minimum value on this interval. Now there are a few different ways to do it with some slight variations, but what I'm going to do is I'm going to find where f prime of x is 0, right? So I'll look at all of those x values, and I'll look at endpoints. It's really important that you look at the endpoints when you are finding absolute minimum or absolute maximum values. In fact, whenever I got used to these problems, I used to write a notice to myself, check endpoints every single time I saw the word absolute minimum, absolute maximum, just so that I remember to do that, because they like to trick you on that if you don't do that. So let's find f of x, f prime of x, right? So I'll write the product rule here. So f prime g plus fg prime, however you want to remember it. That's how I remember it. So the derivative of our first function here is just going to be e to the x itself. I'm going to move this right here. F prime of x. So e to the x is f prime, and then g is just going to be cosine x, right? Okay. And then you're going to add a f, so that's just e to the x again, and then g prime will be a minus sine x. Going to do a quick rewrite here, and I'm going to factor out e to the x so that just so it's a little simpler, and also it'll come in handy a little bit because we want to find where this is 0, right? So now we set this to 0. So f prime of x is 0. So we set this value here, e to the x cosine x minus sine x equals 0. Okay, so first we check where e to the x is 0. Now e to the x is always positive for all x. Right? If you want to look at the graph of e to the x, it looks something like that, right? It'll never actually touch the y-axis on the left side. So that's never 0. Okay, that makes things simpler. Now we just have to worry about cosine x minus sine x being 0. Okay, so I'm going to add sine x to both sides. So now we're just trying to solve this equation. So now we look at our unit circle, right? So look at, okay, well, where's cosine equal to sine? Well, they both will have the same signs right here and right here. And remember, we are working in 0 to 2 pi. How convenient, right? They have limited the x values for us. So this value right here in the first quadrant will be a pi over 4. And then over here will be a 5 pi over 4. Right? This is sort of pre-calc review here. So now x will be pi over 4 or 5 pi over 4. Okay, so we have found out some of the candidates, right? But remember, right, we also have to consider the endpoints 0 and 2 pi. Do not forget to consider the endpoints. There's one thing you take out of this video. You have to consider the endpoints when you are taking when you're finding an absolute extrema. So now we're going to test all of these. So these are the candidates, right? Okay, and maybe the most organized way to do this is I'm going to have a table. So we'll have what x is, f of x is. Now all we've got to do is find the absolute minimum, right? Not maximum, but minimum of the function f. So let's remind ourselves what this is, e to the x cosine x over here. Now I've got to do some plugging in. It may not be as bad as it looks. So f of 0, right, so it'll be e to the 0 cosine 0. That'll simplify nicely to just a 1, right? So that's pretty easy, it's just a 1. Alright, now 2 pi. So f of 2 pi will be this random e to the 2 pi, and then we've got a cosine 2 pi, which we can simplify to just e to the 2 pi. Okay, I mean, that seems pretty big. Right, I don't think that's going to be a maximum. I mean a minimum. And now we've got to do pi over 4. Let's figure out what the value will be. You've got e to the pi over 4 and then cosine pi over 4. And right, that will simplify to e to the pi over 4 multiplied by root 2 over 2. Right, okay. So I'm just going to write that down. Okay, and now our final candidate here that we're testing is going to be 5 pi over 4. So let's test that. And intuitively, that's going to be a little bit promising because I know that the cosine value will be negative here. So hopefully we'll get a negative value. So we had e to the 5 pi over 4, and then we've got a cosine 5 pi over 4. Okay, right? That's going to be a minus root 2 over 2 because we're in this part of the unit circle. And then we've got your e to the 5 pi over 4. And you can do a little bit of simplifying here, right? What you can do is rewrite this 2 as root 2 times root 2, and then cancel those out like that. So it becomes 1 over root 2 minus 1 over root 2, and then you've got e to the 5 pi over 4. And note, you don't actually need to know the values of any of the other candidates because they are all greater than 0. So, I mean, they don't really matter, right? We're looking for the absolute minimum. So definitely, this is going to be bigger than 0, right? I mean, this is going to be the absolute minimum. So the absolute minimum is this value, absolute minimum, right, by the candidates test. So the candidates test is what we just did, where we find a bunch of candidates by setting f prime x equal to 0. By the way, they will most likely give you 1 point. This is an FRQ question, and they'll give you 1 point for setting f prime x equal to 0. So at least do that if you do anything. And then you've got to include the endpoints. Right, again, common mistake to not include the endpoints. So include the endpoints 0 and 2 pi. We tested them first here. And yeah, that's pretty much it for this problem. Move on to the next one. Alright, let's get going with the second problem here. So we have this differential equation. We've got this initial condition. So this is just a point that is a point on this curve here. And then we're looking at whether f has a relative minimum, maximum, or neither. Okay, so first thing that would come to my mind if I was solving this problem is, well, let's use the first derivative test, see where dy dx, how dy dx changes close to x equals 2. But the problem is you can't really find out what dy dx is, right? They don't give you what x and what y is near f of 2. They obviously give you the y value at x equals 2, but other than that, they don't give you anything. For those of you who know how to integrate a little bit, this is not a separable differential equation, so this will be impossible to solve for right now. So we're going to look at the second derivative test. And so what the second derivative test is, provided that the first derivative is 0, then the second derivative, or the concavity, will determine whether it's a relative minimum or maximum. So if it is positive, then you've got a relative maximum, relative or local, however you want to say it. And then If you've got a negative second derivative, then you've got a relative minimum. Okay, so let's apply the second derivative test to this problem. So we're going to implicitly differentiate. So it's a 2, right? dx will just be 1. And then minus dy dx. Okay, cool. I mean, we know what dy dx is. So now we have to check that dy dx is 0 before we do anything. So let's do that. So I'm going to say that d squared, the second derivative at x equals 2, is going to be 2 minus the first derivative at x equals 2, right? And we know that to be 2x minus y, provided x is 2. So we're just going to plug in now. So that's a 2, and what's y? Oh no, do we have a y value? Yes, we do, right? We have this initial condition right there, minus 3. Okay, so that's going to be 4 minus 3. 2 minus 1 is 1, which is not 0. So, since dy dx is not 0, we cannot use the second derivative test to determine whether it's a maximum or minimum, but the important thing is that we know that it's not a relative minimum or relative maximum, right? This isn't like inconclusive in this scenario. If this derivative is not 0, then we know that there isn't going to be, it's not going to be a relative maximum or a relative minimum, right? If you go back to the first question, what were we doing right here when we were finding candidates? We were finding whether the first derivative was 0, and we were checking points where that was true, right? And so yeah, same applies here, even though we're trying to apply the second derivative test. So the answer is going to be neither, right? Because dy dx at x equals 2 is not 0. Alright, so that'll be it for this video on relative extrema. I'll see you guys in the next one. I hope this was helpful.